Let's look at some really interesting kinematics problems. So we're going to start with the pursuit problem. And a pursuit problem is a really common problem where there's an object that's pursuing and then that there's an object that is doing some other task. In this example, let's say we have a cop and we have a robber. Our red dot over here is a cop and the blue dot is a robber. So obviously the robber is not pursuing, the robber is escaping, which is action. So in this case, what a robber is doing is, for this specific problem, it is simply going on the x-axis at velocity v. That is all our robber is doing. Let's make that blue so we can see it a bit better. And then on the other hand, our cop in the red dot is actively trying to take down the robber. So what it does is it actively looks for the robber. So I mean, not actively looks, but it aims its velocity at the where the robber is. So in this case, it has velocity. Its velocity is aimed towards the robber upwards. However, if the robber happened to be over here, then the cop would be pointing its velocity over there. So that is the setup of the problem. Now we can get to how to solve this problem. At first, we'll do a simplified version of the problem where we have both of them are traveling at velocity v. The cop is traveling at velocity v, and so is the robber. So what we're trying to find in this first part is after a long time, they're going to end up being on both. They're both going to end up being on the x-axis, and then there'll be a set distance d away, and they'll both be going at velocity v, and the distance d won't change. What we want to find is, what is that distance d? So pause the video here and try to think about the problem and solve it on your own. When you're ready, unpause the video and we'll go through the solution. Okay, so let's start. So the solution goes, this most important part of the solution is to know one important thing. So I'm going to go through how I would notice it, and then once you're become more experienced, it'll become easier to note and find once you see the problem immediately. So first thing I want to do is, what's the most complicated thing about this problem is the fact that the cop's velocity keeps changing its direction. So I was trying to find some key things about this velocity, like its direction, and mainly is just its direction, right? So, and we also need to find the distance from the robber, the distance between the cop and the robber. So let's note down a few things now. Let's say that the vector from the cop over here to the robber over here, this vector, let's call this vector r. Okay, and let's just label that's the vector. I'm probably not going to do that in all the other equations because it's a lot of work to do that, but just remember r is a vector. And now what we're going to do is we're going to see what r is in terms of variables and whatnot. So let's say that so first of all, let's also label rx actually, and ry, and then also, actually that should be pretty much it. So let's first start off finding some equation for r of x. R of x is obviously the x component of the vector. So let's say that the situation ends up looking something like this, where the cop is over here, its velocity is pointed that way. Why is that so thick? Its velocity is pointed that way. And then the robber is over here and its velocity is pointed that way, like usual. Okay, now in this scenario, we label this distance as r of x, distance is r of y, and this is the vector r. Okay, so that's r of x. So now we try to find the change in x per unit time. So we'll say that drx, so actually the change in r of x will be equal to since the robber will move v times delta t in a time of delta t because it's always going in a straight line in the x-axis, while in a small time delta t, the cop will move forward at v cosine theta delta t, where theta is this angle over here. Why is this true? Well, it's simple vectors, because the velocity is traveling at a vector of angle theta to the horizontal. Its horizontal component is v cosine theta. So for a time delta t, he approaches the robber at a speed. He approaches the robber of a small distance of v cosine theta delta t. So now we found what delta r of x is. Let's also try finding what delta of r of y is. So delta r of y is negative v times sine theta. And you can find that it's the same way as we found, times delta t. Same way that we found the first one here. Okay, now let's find what the change in r is. So this becomes a little more complicated. So first off, what we can see is that initially, let's ignore the robber's motion for now. The cop changes its r by negative v delta t, right? So delta r, which is just the distance, not the vector, so the magnitude of r is equal to initially negative v delta t from the cop. Then the robber also moves in this direction. So how does that affect it? Well, let's say we call this distance. So this distance is v delta t. And then let's do that in a different color. This is r plus delta r. So if I shift this diagram a bit to another place where we have r, v delta t, r plus delta r, we can find delta r using the law of cosines. So this angle is 180 minus theta. And now, using the law of cosines, we find that r plus delta r squared will be equal to r squared plus v squared delta t squared minus 2r v delta t cosine 180 minus theta. Okay, so we can expand this. Out, and we can cancel away v squared delta t squared because delta t is really small, so that term is really insignificant. And the same thing, when we expand this out, we'll get delta r squared. So it just ends up becoming r squared plus 2r delta r is equal to r squared plus 2r v delta t cosine theta, because cosine of 180 minus theta is negative cosine theta. Now we can cancel out r squared. We can divide by the r's on both sides, actually 2 r's on both sides, and we end up with this. Delta r is equal to v delta t cosine theta. So that's how much r changes by because of the robber. And this is positive, notice, because the robber is going away from the cop. So now we can add v delta t cosine theta. If you're confused on why we were able to just cancel the v delta t squared, v squared delta t squared, or the delta r squared, it's because when we do this in terms of calculus, these are not deltas, but these are little small changes called dt or dr. And because they're so small, when you square them, it's really, really, it is completely insignificant to the equation, so we can just cancel them out. It's not even an approximation at that point. Okay, so now you'll notice something very interesting. These two are exact negatives of each other. Now here was the important thing to note. What we note is that delta of the magnitude of r is equal to delta rx. So is equal to negative delta rx. In other words, delta magnitude of r plus delta rx is equal to 0. And by integrating, we would actually find that r plus x is then constant. So now, at the end, now we can use this fact to figure out the distance d at the end. The distance d at the end, r is just the same as x because the cop will end up becoming on the x-axis, and then they'll both be following in a straight line. So at the end, we have that r plus x is equal to 2d, but in the beginning, r plus x, oh, and I forgot I mentioned this, let's call the distance from here to here initially a, and then initially r plus x is equal to a, because x is 0, but the distance r is a. And let's put magnitude signs to make this more clear. And now we can solve for what d is, basically, because now we have that 2d must equal a, so d is equal to a over 2. So this, what we just solved here, is a really common example of a pursuit problem, and this is really helpful for tests like the F equals MA or USAPhO.